Okay, so today we're going to get started in the book. Getting started, right? Now, if you're like me and like most students, when you see the professor come in and put up a PowerPoint presentation, what goes through your mind? Crap! I hate it when they use PowerPoint, right? Because you students think, well, I can't keep up. I can't get it all down in my notes before he hits page down and goes to the next slide. Don't worry about that, right? Two reasons. First of all, it's in the book, right? These slides are taken straight from the book. Plus, I will post these slides for you on D2L. So if you miss something in your notes, don't worry about writing down everything that's here. What you should write in your notes are the things that I say that you think, oh, I should probably remember that, or you know, the insights into it. But just pure definition stuff, don't worry about getting that in your notes. It's in the book. So there is, unfortunately, in statistics class, a lot of vocabulary problems, or vocabulary words that you have to learn, right? It's just the way it is. They're in the book, and they're bolded, or they're put in a colored box, or they're in the margin. Somehow they're set off as being important, right? So if you don't get all the definitions down off of the board or off of the screen, don't worry about it. You can go back and fill them in later, right? Sometimes it's better just to listen. Right? Okay. Anytime you teach a course called statistics, I guess it should start with a definition of the word statistics. So what do you think that word means? And it's kind of a trick question. It's got two meanings, right? One meaning is that you have a class called statistics, which means you're going to learn about the field of statistics. So it's a class of mathematical procedures that are used to analyze data. A field of study, like biology, like mathematics, statistics. Right? But it also has a more detailed meaning when we refer to actual collection of data. Okay, so we're going to go through a bunch of definitions here in a minute, but statistics, anything that is a statistic is a numerical measurement taken from a sample. Right? So if I measure the height of everybody in this room and I compute the mean height, that's a statistic. Okay? So it kind of has two meanings. The broad meaning as a field of study, that you won't really have to know. That's statistics. I got to take statistics. But you should know, you will be expected to know the difference between a statistic and a parameter. Okay? And so I'll define what parameter is in a minute. Here are the two definitions that I just talked about. So again, don't worry if you didn't get them down in your notes. So the most important points in section 1 are here and on the next slide. Vocabulary words. Population. Okay, what do you think of when you hear the word population? People. Okay. And what does it mean when somebody says the population of Topeka? Okay.
Well, it really matters more what you're trying to say. Context.
Okay, and that's the point I want to make, is it kind of depends on the context a little bit. Most people, when they hear, what's the population of Topeka, they're thinking a number. That means how many people live there. And it does mean that. But in statistics, it's a broader term. So population is just the collection of all of the subjects, and they don't have to be people, that you're interested in studying. Okay? So it says a particular group of interest. It might be people. It might be corn stalks. It might be tubes of toothpaste. Right? Whatever it is that you're interested in studying, the collection of all of those, that's your population. Right? So population you ever see Venn diagrams when you were in some other math class, right? So think of the population as being the big universe or whatever. Then a sample, it's on the next slide, but a sample is a subset of the population that you can actually study. So down here at the bottom, it says a census is a study in which data are obtained from every member of the population. Right? Now again, that word you hear a lot. Every 10 years in the United States, by law, they have to take a census of the United States. When they use that word census, what are they doing? What does it mean? They count every single person in the United States, right? They count them. But it actually, that word census has a broader meaning than that. What it means is you collect data on every member of the population. You don't just count how many there are, but you actually measure whatever it is you're interested in measuring on the whole population. So if I have height as the variable that I'm interested in, then a census would be to measure the height of every person in my population. Now, depending on what the population is, remember it's a group of interest. Whatever my interest is in, that defines my population. Usually your population is so large you cannot do a census. It's not practical. If I'm interested in adult males in the United States, I can't take a census of their heights. It'll take me the rest of my life to line them all up and measure them, right? But if my population is the males in this room, they're the only ones I'm interested in, then I can do that pretty easily. I can take a census of that. Okay? So I use two other words, data and variable. They're kind of self-explanatory, but we need to define them. Data are counts or measurements or observations gathered on a specific variable from a subject in the population, right? So, variable. What is a variable? Oh, I had algebra. I know what a variable is. It's an X or it's a Y, right? In algebra, you use the term variable as a placeholder for some unknown value that makes this equation work out, right? But in statistics, it's sort of the same thing, but it's the word variable has as its root, what's the root of the word variable? Vary, right? So it's a measurement that varies from subject to subject to subject, right? So it's a variable. So if I measure your height, that's a variable. If I measure your weight, that's a different variable. If I measure your gender, that's a different variable. So each subject has lots of characteristics that we can measure, and each of those is called a variable, right? So a value or characteristic that changes among members of the population. Yeah?
So in statistics, is there ever a constant?
Yes. There are things that are constant, right? And I will remember to point that out as we do this, right? So I said a minute ago what a statistic was, the second definition. It's a characteristic that's computed from a sample from the population, right? That's called a statistic. If I could measure that same thing on the entire population, it's called a parameter. So a parameter is a numerical description of a population characteristic. It's mean or median or standard deviation or something like that, or the percent of people in the population who favor Donald Trump, right? That's a parameter. Now, if it's not possible to take a census of the whole population, you'll never know what those things are. So what we do is we draw samples and we try to estimate the parameters. So statistics are sample estimates of parameters. If I want to know the mean height of adult males in the United States, what do I got to do? It's a trick question. You can't know that number. It's impossible to know that number. The mean height of adult males. But I could estimate it, but I'm never going to know it exactly. Think about that problem of getting the true actual value of that parameter. The mean height of all adult males in the United States. So I round up all the adult males in the United States. There's only probably 150 million of them. So I line them up. And I get out my tape measure and I start measuring. That's going to take me a long time. So I'm going to get some help, but still, it's going to take a long time. But by the time we get to the last guy in the line, what's going to happen?
First person's going to grow.
Well, it might not grow if they're adult, but somebody's going to die, right? And then somebody else is going to age into that group, right? Somebody's going to have their birthday before I get done, and now they're 18 or whatever my cutoff is. So it's impossible. So we say a lot of times that parameters are unobservable. Parameters are usually unobservable. Theoretically, you could do it. Theoretically, there is a value for the average height of males in the United States at this instant. But we just have no way to ever observe that, to know what it is. So we take a sample, a subset of the population from which the data are collected, right? So I take a sample from the population of adult males, and as long as I do my sampling in a statistically valid way, then I can assume that it would be representative of the population, and maybe I get a mean of 5'11.3 inches. Right? I'm smart enough to know that, well, that's not going to be the actual value of the parameter, but it ought to be pretty close. So that step of moving from a sample statistic to making inference to a population is called inferential statistics. Okay? So I've got a slide in a minute that talks about two areas of statistics, and I think it's an oversight in the book that they leave out one of them. But, well, I'll save that till I get there. Any questions on these definitions so far? Out of the first section, the last slide and this one, those are the most important vocabulary words that we'll hit. Right, so that's my drawing over there. You saw that. Let's practice a little bit. This slide says, identify the population and the sample in each of these two scenarios. So scenario A, in a survey, 359 college students at the University of Jackson were asked if they had tried the October flavor of the month at the coffee shop. 83 of the students surveyed said yes. What's the population of interest? What's the sample? Eric?
The students at the University of Jackson population.
Okay.
And then the sample of the three.
Okay, I'm going to add one word to what he said. He said the students at the... I'm going to say all the students, just to emphasize that it's all of them. Population is all of them, right? And then the sample?
It's the 359 they interviewed.
Okay, the 359 that they interviewed, that is the sample. So what's the 83? What'd you say? It is a statistic. That's right. It's a sample statistic. If I take 83 and I divide by 359, I can convert that into a proportion or a percent, and that's a sample statistic. So this question doesn't say what are the statistics, but that's what that would be. So it's a common mistake to get confused on which number's which, but the sample size tells you, or the number that is the sample, how big the sample was, that's the tip-off for this is my sample. Population is always all of them. from which that sample was drawn. Okay, survey of 1,112 or 25 households found that 24% subscribed to satellite radio. Population?
All the households in the United States.
All the households in the United States. Okay. They say they take a survey. Now, these questions aren't bothering to say anything about how the survey is drawn. But a minute ago, I said, as long as your sample is representative of the population, right? Well, a big mistake that's made when people do surveys and things is they have in their mind what their population of interest is, but they draw their sample in such a way that it doesn't represent that. It's narrower. Like if I'm interested in households in the United States, but I only sample houses in Topeka, what's my population? All houses in Topeka, but I cannot make inference to all houses in the United States. Right? To get a valid sample to estimate that, I need to have every household in the United States be eligible to get into my sample. Right? What about the 24? That's a statistic. Okay. What's the parameter? What's the parameter that we're trying to estimate? Okay. The percent of people in the United States who use satellite radio. That's the parameter. What's the value of that parameter? We don't know. This is the value in my sample. It's probably a decent estimate of that parameter, but we'll never know that parameter. After an airplane security scare on Christmas Day, the Gallup organization interviewed 542 American Air travelers about increased security measures. The report stated that 78% of American Air travelers are in favor of United States airports using full-body scan imaging on airline passengers. Identify population, sample, parameters, statistics. Population? American Air travelers. American Air travelers. Right? Sample? The 542 that actually answered the question. Right? What's the number 78? Is that a statistic or a parameter? It says 78% of American Air travelers, which is the whole population, so that is a parameter. Now, where did they get that number? They made it up, right? Because they never know the true value of that parameter. But what they did, this is most likely, this is how things get reported a lot of times, which is not quite correct. They should have said, the report stated that in our sample, 78% said this. So we make inference that in the population, it's 78 plus or minus a little bit of wiggle room. Right? Now, this is a great semester to be taking statistics because it's a political year. Right? It's a leap year. So national presidential election. So you're just inundated with survey results every day on the news. It's the latest poll in Iowa says, right. But if you look at the bottom, when they print those things, there's always a little thing that says margin of error plus or minus 4% or plus or minus 3% or whatever. That's the wiggle room. Right? So when they make inference from a sample, they should include some indication of the margin of error. How close do you think you got to the true value? That's what margin of error is. won't define that today, but it won't be very long before we get a definition for and a way to compute that margin of error. Okay, so here's the solution. The value 78% refers to all American air travelers, thus it is a parameter. Okay, so here's the slide I was talking about a minute ago. This slide gives 2 of 3 sort of branches of the field of statistics. Descriptive statistics and inferential statistics. The one that should come first, which they left off, is design. So the branches of statistics design of studies. I think I mentioned on the first day of class that I still do a lot of consulting out. I do statistical consulting out in industry and on research teams and things. This is where I spend most of my time as a consultant. This is what is most valuable to whoever's doing the research, right? They need to know, okay, I want to know, does this drug work better than the drug that's being marketed now, right? If they don't study that in a statistically valid way, then they're never going to be able to answer that question with any kind of certainty. So they need to talk to a statistician to help design the study so that in the end they can make valid conclusions, right? So design is the planning of research studies to provide valid inference. I'm having marker trouble today. Let's try this again. Okay, so provide valid inference. Well, the word valid, everybody knows what that means, but inference is inferential statistics, and that's, I said this before, it involves using descriptive statistics from a sample to estimate population parameters. Well, if that inference, if the study was not planned correctly in the beginning, that inference that you make isn't going to be valid. If I take a really bad sample and estimate that 88% of American voters support Donald Trump, but it's a biased sample, then my statistic that I'm using to estimate my parameter isn't going to be valid, right? That's not a valid inference, right? So this whole idea of designing the study in an appropriate way is a very important part of statistics.
In that example, would that usually happen with it one demographic selected?
Exactly. Yeah. Now this discussion, I'm not going to go down the road, although that's my passion, is design questions. That's sections 1.3 and 1.4. And we're going to talk about valid ways to collect data, right? So descriptive statistics are, now that you've collected data, summarize it, right? So descriptive statistics is number 2. Somebody snuck into my office and replaced all my markers with bad ones, I guess. Oh, there's a good one. So descriptive statistics are just summarizing the sample that you took, right? So summaries of the sample. There'll be statistics that you compute, like the mean, the median. There might be graphs that you produce. Here's a bar graph showing this many people in this demographic, this many people were in this demographic, or so on, right? That's all descriptive statistics. And then inferential statistics then makes the leap from the sample to the population. So this uses statistics, sample statistics, to infer parameters, to make estimates of what are parameters. Okay, we've got a sentence or two here that was actually published in a report. AOL had 900 journalists, 500 of them at its local patch news operation by the end of 2011. Bloomberg expects to have 150 journalists and analysts for its new Washington operation, Bloomberg Government. Okay. Identify the descriptive and the inferential statistics used in this article. What are descriptive statistics being quoted there? Okay, they had 900 journalists, 500 of them were at a local news operation, and so on. What's inference? By the end of, and this is, did it say when this was published? It was published during 2011, so by the end of 2000, so they're looking into the future, that's making inference. Right? So by the end, we expect to have 150 journalists. Okay. Any questions over section 1.1? Like I said, it's kind of all vocabulary. It's boring to go through, but we got to get through it. You have to learn the words so that you know what we're talking about in class, and you know what they're writing about when they give you homework questions. So now let's talk about the data itself. I've got, again, a bunch of definitions, vocabulary words about different types of data, and then we'll take a look at your Google spreadsheet that you're filling in for me and see if we can identify some of these things. So the first thing, when we talk about data, we had that definition earlier. That's just values that we get when we measure subjects in our sample, right? So we can divide, first of all, into qualitative data or quantitative data. And if you have trouble remembering definitions of words, it's helpful often to go back to the root of that word, right? So what is the root of qualitative? Quality, right? So what is a quality of the subject? So basically, qualitative is categorical. That's, to me, a better word. But qualitative is categorical data. Or an even simpler way of saying it, grouping variables. Okay? Let me go ahead and click the link and pull up the Google Doc. They sure want to sell me something. So let's see. The first person from this class that got their data in was JMI. Who's that? What's your name? John. Okay, John. So John got his data in first. He beat the rest of you. Way to go, John. Let's scroll. Uh-oh. Maybe we won't scroll. Anyway, we can see it. Give me a variable that is qualitative. What'd you say?
Health rating.
Health rating. Qualitative? Okay, it is. It's a quality, right? It's a category, right? Remember, these are just numbers. They're just placeholders for poor, fair, good, very good. Right? Give me another one that's qualitative. Gender. Right? So we have a column titled sex. Male, female. That's a quality of the person. Right? Any others? Exercise status and smoke status. Those are qualitative. Okay? So they're grouping variables. I can group people into what gender they are, or whether or not they smoke, or so on. Okay? All right, the next term they had was quantitative. What's the root of quantitative? Quantity, right? So quantity, that word makes you think of what? How much? How much of something? So those are measurements, numerical measurements. Okay, so let me go back to the slide. Counts or measurements. So if you count the number of eggs that your prize chicken lays every day, right? That's quantitative data. You're quantifying how many eggs, right? From our data that you're collecting, give me a quantitative variable. You said, was it you? What did you? Age, okay? And then you said shoe size. I'm going to come back to shoe size in just a minute, because shoe size is in what I call the gray area. It's a little weird, but age is definitely quantitative. What are you quantifying? How many years they've been alive, right? What's another quantitative variable that's in there? Nobody? Pulse is quantitative, right? You're counting how many beats per minute, right? One more. Height. Height is quantitative, right? Okay, so once we make the distinction between quantitative and qualitative, we can further break down these things into other subcategories. Quantitative data can be broken into continuous data or discrete data. In continuous data, it says up here, are quantitative data that can take on any value in a given interval and are usually measurements. Right? I can't think of one that would not be measurements, but they say usually. Always is a strong word to a statistician. So it's hard to know for sure, but can take on any value in a given interval. What about height? Would that be continuous? Yeah, that's continuous. Right. If somebody asks me how tall I am, I tell them I'm 5'9", 69 inches. Do you think I'm really 5'9"? Exactly? No. I'm going to be, well, I'm getting old, so I'm probably a little shorter than that now. Right? So I probably shrunk. But I'm not going to be exactly 5'9". So what they're referring to there is, are decimal places possible, and any value on those decimal places, is that possible? Right? So any value is possible within an interval. Any value is possible. Decimals to any number of places. If I had an accurate enough measuring device, I could measure your height to the nearest tenth of an inch or the nearest hundredth of an inch. Or if I had one accurate enough, I could go to the nearest millionth of an inch. Not sure why I would need that kind of accuracy, but theoretically that's possible. So that's continuous data. All right? What about my chickens laying eggs? Is that continuous? How many eggs does your chicken lay? You can't. You're not going to go out there and find a half an egg, right? Or 1.8 or 1.883, right? So not any value is possible. So that is discrete data. Quantitative data that can take on only particular values, and they're usually counts, like counting the number of eggs, right? So what about heart rate? Continuous or discrete? It's discrete. At least the way we collected it. It's discrete. I've never seen heart rate out to decimal places, right? It's beats per minute, and you're counting how many beats there were, so you can't really say, well, I had 62.4 beats in that 1 minute, right? So that would be discrete data. Shoe size. Continuous? Nope. It's got decimals. You said decimals.
You can't have this 11.2 shoe size.
Right. You said continuous. Continuous says any value is possible. So if any value is not possible, because 11.2 is not possible, then it must be discrete. Right? So even though it has decimals, that would be discrete. So only, I didn't write down what's up there, but only particular values are possible. And then it helps me to just think gaps. There's gaps between the possible values. At least theoretically, in continuous data, there are no gaps. Any value would fill in, right? But there's gaps. Now, shoe size, I said, is kind of in the gray area. So think about shoe size for a second. To be discrete, it first has to be quantitative. What are you quantifying? Ooh, no, that's not quite right. It's close. Number of inches. I wear a size 9.5 shoe, but my foot is not 9.5 inches long. I know because I measured it. So shoe sizes, yeah, quantifying how long the foot is, but the scale is weird, right? In fact, females have a different shoe size scale than males do. And Europeans have a different shoe size scale than the U.S. has. Right? And there's like 6 or 8 different ways, right? Different scales that they measure shoe size. So shoe size is a little bit weird. It's hard to say what the units are. I don't know what the units are. Usually quantitative data, there's some kind of unit there. Either it's count, which the units are obvious, or it's like height, which is inches. Right? What are the units? But shoe size, I don't know what units. They're not inches. They're almost, I think originally they were inches, but then it kind of morphed because they found people buy it more if the size is a little less than what the inches are, right? Because it makes them feel better. I don't know. But. Okay? So, let's go. There's one more that I don't think they have. Oh, there it is. They talk about levels of measurement now, and they've dropped this word ordinal as a level of measurement, but I really think it ought to be at the same discussion with continuous and discrete. And it goes under here. Ordinal data is categorical data or qualitative data, but there's a natural order to the categories. Okay? And the most common example of that are rating scales. Right? So, ordered categories we call ordinal data. So let's go back to here. Which one of those is ordinal? This is our survey that we collected. Age is not ordinal.
Health rating.
Health rating. Health rating is ordinal data. And again, these numbers, people get fooled. Oh, there's numbers. That's quantitative. No, it's not quantitative because those numbers don't mean anything. Right? I could have just as easily reversed and said, put a 5 down if they say poor, put a 4 down if they say fair, and it wouldn't change anything. Right? So the numbers are just arbitrary. You're not quantifying anything with these numbers. They're just names of categories. So it's categorical data. Poor, fair, good, very good, and excellent. But there is an order I can put them in. I can say, well, if they say poor, they're worse off than somebody who says good. And they're worse off than somebody who says excellent. So I can put them in an order. Okay? Think of another example of ordinal data besides a rating scale. Can you think of one? It's okay, I can wait. Something that's just categories, but there is a natural order to those categories. Grades. Very good. A, B, C, D, and F. Right? They're just categories. Now, a lot of times we have a numeric measurement behind there that then gets collapsed into a grade, but not always, depending on what subject you're studying. But grades are definitely ordinal. What about classification in school? Freshman, sophomore, junior, senior. Right? Now, some people say, well, but that's what year, freshman, it's your first year. So, well, not always. Well, it's based on how many hours you have. So, again, it can be thought of as a numeric variable that's being collapsed into categories. But just purely as categories, that's what they are. They're categories. But there's an order to them. So that's ordinal data. Okay? I got to remember which. Yeah, here we go. So they have this term nominal level, and you have term used nominal for just another word for categorical data. So you have categorical data where you can call that nominal data, but it's said to be at the nominal level because what's the root word of nominal? This one's harder. Nom, which is French for name, right? So it just names things. So nominal just names things, right? So that's the level of measurement of categorical data. Then we have ordinal, and then for quantitative data, the levels of measurement. There's two levels of measurement: interval and ratio. Right, so interval data, it says quantitative data that can be arranged in a meaningful order and differences between entries are meaningful. Okay? So today when I was driving down here, my car thermometer said it was 23 degrees. Right? On Sunday, it said it was 15 degrees. The difference between 23 and 15, which is 8, that makes sense, right? That's an okay thing to do. But health rating, this one guy said he was in excellent health, so I put a 5 in there. And somebody else said they were in poor health, so I put a 1 in there. And the difference, 5 minus 1, is 4. Does that make sense? No, because those numbers are arbitrary. If I'd have used 10, 20, 30, 40, 50, the difference would have been 40 instead of 4. So interval, it makes sense to take difference, to make an interval out of those numbers, right? But what it does not make sense to do is take ratios of temperatures. And think about that for a second. And I hear people do this a lot, but it was the wind chill on Sunday. Well, when I got up Sunday morning at my house, it was 1 degree, right? It was 1 degree above zero. And so then a little bit later, an hour later or so, I looked again and it was 2 degrees. Holy cow, it's twice as warm as it was a while ago. Because 2 divided by 1, if I make a ratio, 2 over 1 is 2, it's twice as warm. Does that make sense? No, it doesn't make sense. We're measuring with temperature. We're quantifying something. Oh, come on. You've had to have some science at some point. What does temperature measure? Heat. Thank you. Heat. Right? When it's 2 degrees, is there twice as much heat as there was when it was 1 degree? No. The distinction is interval data does not have a natural zero on its scale. What's the zero for Fahrenheit temperature? Where did they get that? Where did they decide to place zero right there? It's a trick question. It was arbitrary. What about Celsius? What's the zero in Celsius? The freezing point of water, which is 32 degrees Fahrenheit, right? But zero doesn't mean no heat on that scale. There's still heat. It's just not a whole lot of it to a human, right? What scale of temperature does have a zero that means none of whatever it is you're trying to measure? Kelvin. 0 degrees Kelvin, if I said it's 1 degree Kelvin, and then a little bit later it's 2 degree Kelvin, it's twice as warm. There's twice as much heat as there was before, because that's what it's measuring. But if the zero is arbitrary, like our years, this is the year 2015, the zero is an arbitrary placement, right, based on the birth of Christ. But it doesn't mean no time has gone by at year 0, right? So, interval, arbitrary 0, ratio a 0, that means truly there is none of whatever you're measuring. All right, so we'll quit there. That finished section 1 and 2. So homework over 1 and 2 will be due Monday night by midnight, and the data collection is due Monday night by midnight. I've already got a lot of yours, but still a lot of you need to do it. Have a great weekend.